Welcome to EPG Pathshala. This module is about the atmospheric properties. Earth's atmosphere is gaseous envelope that surrounds our planet. This atmosphere is composed mainly of nitrogen and oxygen with traces of carbon dioxide, water vapor and other gases, and it acts as a buffer between the Earth and the Sun. And the atmospheric layers vary around the globe and it in response to the seasonal changes. So in this module, we are going to discuss about what is atmosphere, what are the key atmospheric properties, how temperature, pressure, density changes with several factors, what are the thermodynamic properties of the atmosphere, and what are the governing equations of the atmosphere. Atmosphere and its composition. Atmosphere is the gaseous envelope that surrounds the Earth. It approximately extends up to 500 km above. Our atmosphere is composed of different gases. The major ones are nitrogen and oxygen. Nitrogen accounts nearly 78% of the atmosphere and oxygen for 21%. Oxygen can also exist in triatomic form, that is called ozone, which has significant property of absorbing ultraviolet solar radiation. Water vapor, whose abundance can vary from almost nothing in the driest of the locales to about 4% of the atmosphere. It is responsible for the formation of clouds when water vapor condenses into liquid droplets or freezes into ice crystals and precipitation. Additionally, this water vapor is a greenhouse gas and it plays a key role in the heat budget of the Earth. Another significant greenhouse gas is the carbon dioxide that emitted as a byproduct of many industrial processes, and its increasing abundance in the atmosphere is the source of much concern regarding the future climate change through the global warming. Now we will see what are the atmospheric properties. Temperature. Temperature is the measure of thermal or internal energy of the molecules within an object or gas. We can measure the temperature of an object using either direct contact or remote sensing. The temperature of air is closely related to other atmospheric properties such as pressure, volume and density. Another atmospheric property is the density. It measures the heaviness of an object or how closely packed the substance is. Density is related to both the type of material that an object is made of and how closely packed the material is. The third property is the pressure. It is the force exerted over a given area or object, either because of gravity pulling on it or other motion the object has. The molecules in the air produce pressure through both their weight and movement, and this pressure is connected to other properties of the atmosphere. Another property of atmosphere is humidity. It is a measure of the amount of moisture in the air. It tells you how comfortable it is to be outside and if there is enough moisture to create clouds and rain. The variations of temperature. In the atmosphere, the temperature is related to the volume, pressure and density. Temperature is inversely related to density but directly related to pressure and volume. This means when temperature increases, density decreases and volume and pressure of the gas also increase. So air that is warm and dry will tend to rise when surrounded by cooler air because warm air is less dense than the cooler air around it. The temperature controls planting dates and the growth of plants as well as insect pests and the crop diseases. It is an integral part of weather. The temperature also determines the type of precipitation, that is rain or snow or sleet, that might occur if you are in a location that is experiencing near freezing conditions. Temperature is a measure of how much internal energy an object or gas has. For example, a gas with fast moving molecules feels hot because when that gas touches something that is cooler, some of the energy of the hot gas is transferred to the cooler object and the cooler object responds by warming up. If there are two objects with different temperatures, energy flows from the warmer object to the colder object always. The atmosphere is a mixture of gases and follows the principle of fluid dynamics. Convection is a form of heat transfer which takes place in the fluids. It works because in a fluid chunks of matter or the parcels can move up or down with respect to the rest of the fluid as they are being heated or cooled respectively. The process of convection are, however, governed by the laws of thermodynamics. Understanding these laws help us to quantify these processes, making predictions on the formation of clouds and fog, and explain how the vertical profile of temperature in the atmosphere is determined. The thermodynamic properties of dry air, the adiabatic temperature change. The equation of state, the ideal gas law. If air contains no water, it is called dry air. And the state of a parcel of dry air is described by three properties: temperature T expressed in degree Kelvin, 273 degree Kelvin is equal to 0 degree Celsius. Pressure, that is P, that is force per unit area expressed in Newton per meter square, and density, that is rho, that is mass of a unit volume in kilogram per cubic meter. In a gas, these properties are related by a relatively simple physical law that is called ideal gas law. It is known as ideal because it is not exact, albeit quite accurate for most applications in the meteorology. And this law states that P is equal to rho RT, where R is the coefficient which is called gas constant. It does not depend on either P, rho or T. The gas constant depends only on the composition of gases that make up the air. Every gas has its own gas constant. Since this composition for the dry air is roughly constant throughout the most of the atmosphere, R of air is constant and equal to 287 joule per kilogram per degree Kelvin. To understand the equation of state, it is assumed that we have a fixed mass of air enclosed in a container with rigid walls. Hence, it has a fixed volume. If we warm the container, say by putting it over a flame, the temperature of the air, that is the kinetic energy of the air molecules, will rise, and the pressure, that is the force exerted by these molecules on the container wall, will increase. The density of the air will not change since we are not increasing the amount of gas in the container or the volume of the container. The ideal gas equation states that the increase in pressure is directly proportional to the increase in temperature. Now, if we replace the rigid wall of the container with flexible ones that are allowed to stretch freely if the pressure inside rises above that on the outside. In that case, when we raise the temperature, the pressure inside will remain constant and equal to the outside pressure, but the container's volume will increase. This means that density will decrease because the mass inside does not change, but the volume increases. So, m by V is equal to the density. Thereby, the density decreases. The ideal gas law states that density decrease will be inversely proportional to the increase in temperature. The first law of thermodynamics and adiabatic expansion. Let us remove the flame that heated our flexible wall container and put it in a chamber where the pressure can be controlled from the outside. It can be lowered or raised as well. What will happen to the density of our air parcel when we lower the pressure surrounding our container? What will happen to its temperature? Here also, the pressure on both sides of the flexible container walls will equalize. As the outside pressure drops, the container will expand and pressure inside will drop by the same amount. The density of the air parcel in the container will decrease as well. That is in agreement with the ideal gas law. But what the ideal gas law cannot tell us is what will happen to the temperature. To find out, we need to consider the first law of thermodynamics. It's a physical law that extends the principle of conservation of energy to include the concepts of heat and work. In thermodynamics, the simplest form of energy conservation is the balance between internal energy, the kinetic energy of the body's internal molecular motion, which is proportional to its temperature, and the amount of heat added to the body minus work done by the body on its surroundings. As our air parcel expands in response to the lowering of the outside pressure, the force of its internal pressure is moving the walls of the container outwards. When a force is moving an object over a given distance, it does work. Thus, the expanding air parcel does work on its surroundings. This work must come at the expense of internal energy. Remember, heat is neither added nor taken away from the parcel in this experiment. Thus, the molecular motion within the parcel will slow down and the parcel temperature will drop. The expanding parcel will experience not only lowering of its pressure and density but also of its temperature. All the three state variables, pressure, density and temperature, will remain in balance as described by the ideal gas law. And the process described above is known as adiabatic expansion. It implies the change in parcel density without the exchange of heat with its surroundings and its consequential cooling. The opposite will occur when the parcel is compressed. Adiabatic compression always leads to warming up. Using the equation of state, the first law of thermodynamics and the hydrostatic equation, using the equation of state, the first law of thermodynamics and the hydrostatic equation, we can find that the rate of adiabatic temperature change in an ascending air parcel is constant. Here, the gamma D is equal to minus delta T by delta Z, which is equal to 9.8 degrees Celsius per kilometer. Note that this gamma D is defined as negative of the actual temperature change, so that the gamma D is the amount of cooling that the rising parcel experiences. Sinking air will warm at the same rate as it is being compressed by the increasing pressure. This figure shows the vertical variation of the Earth's temperature. Here, you can see the regions where the temperature increases with height and regions where the temperature decreases with height. You can see the different layers of atmosphere that are troposphere, stratosphere, mesosphere and thermosphere. In the troposphere, with the height, the temperature decreases and it increases with the height in the stratosphere. Again in the mesosphere, the temperature decreases with altitude, and thereafter in the thermosphere, the temperature rises. Variation of the density. The technical definition of density is mass per unit volume. Generally, density describes how tightly packed something is. An object with a lot of material in a small space is denser than an object that has lots of airspace included. In the atmosphere, gas that is less dense has a lower concentration of molecules per volume than a denser gas and will tend to rise compared to the air around it. Why do I care? When planting crops or plants, soil density is very important. If the soil is packed too tightly, the plant or crop won't be able to absorb any water or nutrients from the soil and will not be able to grow properly. The density in the atmosphere is also important in the formation of clouds and precipitation. Warm air is less dense than cooler air. Air density varies with the relative humidity, that is, the amount of water vapor molecules in the air. So it varies along with the temperature. Water vapor molecules are composed of hydrogen and oxygen molecules. Hydrogen has a molecular weight of 1.01 gram per mole. The dry air is composed mostly of nitrogen molecules, since the Earth's atmosphere is 78% nitrogen and 21% oxygen. Nitrogen has a molecular weight of 14 gram per mole. In the atmosphere, the density of air particles decreases with height, with more air gas particles remaining near the surface of the Earth. When only taking into account humidity, the dry air is denser than moist air because of molecular weights of the gases. A hot air balloon is a good example of how people work with density. Hot air balloons use the properties of density in order to float. In the base of the hot air balloon, there is a torch that heats up the air inside the balloon. When the air inside the balloon becomes warmer than the surrounding air, the balloon will begin to float. The person controlling the hot air balloon can add more heat to the balloon to reach the desired height. The air inside the balloon needs to cool in order for the balloon to land. The density of dry air can be calculated using the ideal gas law, which is expressed as function of temperature and pressure, where rho is equal to P by R specific T, where rho is the air density in kilogram per cubic meter and P is the absolute pressure in Pascal and T is the absolute temperature in degree Kelvin. R specific is the specific gas constant for dry air and its unit is joule per kilogram per degree Kelvin. The specific gas constant for dry air is 287.058 joule per kilogram per Kelvin in the SI unit. And this quantity may vary slightly depending on the molecular composition of air at a particular location. So therefore, at IUPAC, the standard, that STP, that is standard temperature and pressure, is that is at 0 degrees Celsius and 100 kilopascal, the dry air has a density of 1.2754 kilogram per cubic meter. At 20 degrees Celsius and 101.325 kilopascal, dry air has a density of 1.2041 kilogram per cubic meter. At 70 degree Fahrenheit and 14.696 psi, the dry air has a density of 0.074887 pounds per cubic foot. The variation of pressure. Pressure is force exerted over a given area. In the atmosphere, the molecules in the air apply pressure to everything on the earth, including us. For instance, individual molecules in the air push against tiny areas on the top of our head. The force that air exerts is called the air pressure. The more air molecules that there are above you, the greater the force they exert, so greater the pressure. The pressure is important because it is related to volume, density and temperature. In the atmosphere, warm surfaces can heat the air above them, causing the air to become less dense and to rise. This can eventually result in clouds and precipitation in the areas of rising motion, such as in the center of low pressure system. High pressure in the atmosphere causes the air to compress and sink, which lead to clear skies and calm condition. We all live near the bottom of an ocean of air. At sea level, the weight of the air overhead presses on us with a pressure of approximately 10 to the power 5 Newton per meter square, which is equal to 14.7 pounds per inch square. We are not aware of this great weight because the air presses on us from all the sides, even from our insides, due to the air in our lungs. So we don't feel it. At higher altitudes, there is less air and less weight overhead and the pressure is less. Also, because air is readily compressible, the lower layers of air are compressed by the weight of the air above. Thus, the pressure and density of air decrease at higher altitudes. That's why a helium balloon rises. The pressure on the underside of the balloon is greater than the pressure on the top. This figure shows how air pressure, that is in the y-axis, falls exponentially with increase in the altitude, that is the x-axis. And the mathematical form of this is given in the equation P is equal to P0 e to the power minus mgh by kt, where h is the height above a level where the pressure is P0. M is the average mass of an air molecule. K is the Boltzmann constant, where K is equal to 1.38 into 10 to the power minus 23 joule per Kelvin, and T is the temperature in degree Kelvin. Note that both mgh and kt have units of energy, so the exponent is dimensionless. It's a remarkable characteristic of the exponential function. This equation is true regardless of where we set the 0 of h, so long as the pressure at h is equal to 0 is P0. This equation is not quite correct because its derivation assumes that the atmosphere is isothermal when in fact the temperature of the air varies considerably with altitude. This equation can be rewritten as P is equal to P0 e to the power minus h by h0, where h0 is equal to kt by mg, which is a characteristic height which is called scale height of the atmosphere. The scale height is the height increase which reduces the air pressure by a factor of 1 by E, which is equal to 1 by 2.718, which is approximately 0.368. If you started at sea level, that is P is equal to 1 atmosphere, and climbed a mountain with a height h0, the pressure at a peak would be 1 atmosphere by E, which is equal to 0.37 atmosphere. So at an altitude of 2 h0, the pressure would be 1 atmosphere by E square, which is approximately equal to 0.135 atmosphere. If the pressure change is delta P, it can be measured over some small height change, delta H. Then the scale height h0 can be determined, and delta P by delta H is equal to minus P0 by H0, which is almost equal to the H0, which is equal to minus P0 delta H by delta P. The change of pressure with temperature. According to the ideal gas law, if the volume V and number of molecules N are fixed, then the pressure P is proportional to the temperature T, and the fractional change in temperature is equal to the fractional change in pressure. Delta T by T is equal to delta P by P. Here the T is in Kelvin. The variations of humidity. Humidity is a measure of the amount of moisture in the air. Moist air is air that contains water in vapor form. The moisture in the air is usually referred to as humidity. The average concentration of vapor in the atmosphere is 0.48%. There is another way to appreciate the amount of water in the atmosphere is to note that if all of it was condensed and made to cover the earth uniformly, it would make a layer of liquid 1 inch thick. Air cannot carry unlimited amounts of water. Even in the most humid situation, the concentration of vapor in the atmosphere cannot exceed a few percent. The colder the air, the less amount of vapor it can hold. The largest source of water in the climate system is the world ocean. The water evaporates from the ocean surface to mix in the air. Wet or forest covered land surfaces are secondary sources of atmospheric water. The highest concentration of vapor are found near the surface in the tropics. The concentration drops quite rapidly with height and half the way up the tropical troposphere. It is a fraction of what it is in the near the surface. The vapor concentration also falls off rapidly as we move north or south of the tropical belt, and it is generally higher over the oceans than it is over the land. How to measure water vapor in the atmosphere? There are a few ways to measure the concentration of water vapor in the atmosphere. The one is vapor pressure. It is denoted by E. It is the partial pressure of water vapor molecules in the atmosphere. Partial pressure is a term in thermodynamics of gas mixture. In our case, it is air in the air, the partial pressure, thermodynamics of air. We can break down the air pressure into pressure each of its individual gas constituents would exert, and had all the others been removed. The pressure in an air parcel is the sum of the partial pressures of all the constituents. The smaller the concentration of a gas in the mixture, the lower its partial pressure. However, since molecules of different constituents have different mass, the partial pressure is not directly proportional to the molecular concentration. The concept of vapor pressure is important for understanding the processes of evaporation and saturation. If we hold a parcel of air still over flat water surface, water molecules will escape the surface and start mixing with other gases in the air parcel. This is evaporation. It can happen even if liquid is not at its boiling temperature. Evaporation can only go on until the maximum amount of water vapor that air can hold is reached. At this point, the pressure that the water molecules exert as they are trying to escape the liquid is equaled by partial pressure of water in the air parcel, which is called saturation vapor pressure. Saturation is a process of equilibrium where water molecules cross back and forth across the boundary between water and air, maintaining a fixed concentration in the air. And the saturation vapor pressure is a function of temperature. And we can also measure the water vapor by relative humidity. It is the ratio of actual vapor pressure to saturation vapor pressure, which is expressed as percentage if we multiply by 100. This is a common way to indicate air humidity. Because perspiration plays a very important function in maintaining body temperature, relative humidity figures into consideration of the degree of comfort we have when following our daily activities. And the third way is by the mixing ratio. It is the mass of water vapor in grams per kilogram of air. This is the most common way to indicate air humidity in scientific applications. At the Earth's surface, mixing ratio varies from around 18 gram per kilogram in the tropics to less than 2 gram per kilogram near the poles. And another one is by measuring the dew point temperature. It is yet another way to express the vapor content of an air parcel. The dew point temperature gets its name from the process leading to the formation of dew. In early morning hours and before sunset, when the air is still and the ground is cool compared to its daytime temperature, because it radiated its heat into the atmosphere and the outer space. The air in immediate contact with its cool 2. By conduction. Since the air's ability to hold vapor decreases with the decreasing temperature, any vapor in excess of the saturation value is rejected and condenses as droplets on the ground or its cover. Following this natural process, we can define the dew point as the temperature at which vapor in a cooled parcel of air begins to condense. This dew point can be either lower than if the air is not saturated or equal to if the air is saturated than the actual temperature. Bigger the difference between the actual air temperature and the dew point, the drier the air is. So, to conclude, atmosphere is a mixture of gases and it follows the principle of fluid dynamics. The information on temperature, density, pressure and humidity properties are important for any atmospheric application. The changes in pressure, volume and density properties are interrelated with changes in temperature of an air parcel. Convection is the principal mode of heat transfer in the atmosphere and therefore the changes in the air temperature. Atmospheric pressure decreases exponentially with height from the sea level. The vapor pressure, relative humidity, mixing ratio and dew point are the various measures to represent atmospheric humidity. Thank you.